Okay, so let's unpack this. Think about building something really complex, maybe, a new bit of medical kit or even a huge bridge over a river. You've got all these different people involved, designers, engineers, manufacturers, the assembly teams. How do you make absolutely sure every single one of them understands the plan, the blueprint, exactly the same way, right down to the last detail?
Yeah, because if they don't, if there's any ambiguity at all, you're not just looking at delays or wasted materials. It could be safety, it could be structural failure. Everything's on the line.
Yeah.
That precision in communication, well, it's not negotiable.
Right, exactly. So how do you get that universal, crystal clear technical language? And that's really where British standards come in, specifically the ones for technical drawings. They basically set out the essential rules, the grammar, you could say, the conventions that make sure everyone's genuinely reading the same thing.
Oh.
These are published by the BSI, the British Standards Institution.
And they are absolutely fundamental. Can't stress that enough.
And that's what we're doing today in this deep dive. We've got a stack of sources, articles, research notes, and our mission is to pull out the really important stuff about what these British standards are for technical drawings, and crucially, dig into why. Why are they so vital for getting things built right and safely?
Okay, let's start with the what. What actually are these standards? Our sources, they describe them as this widely recognized set of guidelines, specifications, best practices. They provide the whole framework for how technical drawings should be made, read, managed, the lot.
So it's not just about making a neat drawing, it's about the precise instructions hidden in the drawing. Where do they even begin? Like, what are the real basics they standardize?
Well, they start right at the foundation lines. Seems simple, right? But the standards are very specific about different line types. You've got continuous, dashed, chain lines. They specify thickness and, crucially, what each type means. That's a key insight here. It's not just random. A thick, continuous line, that tells you it's a visible edge. A dag line instantly signals something hidden, something you can't see from that viewpoint. Get that wrong, and, well, you could miss a vital support structure or maybe a hidden component. Big consequences.
Huh. I hadn't really thought about how just changing a line type could mean so much. What about the text, the words on the drawing?
Yeah, that's covered too. Lettering standards. They specify fonts, sizes, styles. And again, it's not really about looks. It's purely for legibility, making sure any notes, any labels are just instantly readable. No confusion. Doesn't matter who's looking at it or where they are.
And dimensions, showing sizes, distances, that feels pretty critical.
Oh, dimensions are arguably the most critical information. The standards have strict rules for placing them, indicating them, how you interpret them. And here's where it gets really specific. They cover how you show tolerances, limits, and fits. Think of that as defining exactly how much sort of wiggle room is allowed in a part size. Tolerances define the acceptable variation, limits are the absolute max and min sizes, and fits define how two parts interact when you put them together, like how tight a shaft fits in a hole. It's absolutely vital for making sure parts made in totally different factories will still actually fit together.
Ah, okay. So it's not just make it 50 millimeters, more like it must be between 49.9 and 50.1 millimeter, that level of detail.
Exactly that. And defining that allowed variation is the language that makes mass production and interchangeable parts possible.
Okay, what about trying to show a 3D object on, a flat 2D drawing? That always seems like a bit of a mind bender.
It is a puzzle, and the standards solve it using projections. They specify the approved ways to do this. Most common are first angle and third angle orthographic projection. There's specific graphical methods. Imagine putting your object inside a clear glass box and then drawing what you see looking straight at each side of the box. First angle and third angle are just different conventions for how you unfold that box onto the flat paper. It makes sure the 2D views accurately show the 3D object from defined angles, no distortion.
Okay, right, the glass box analogy, that helps picture it. And all those little symbols you see, like for welding or maybe how smooth the surface needs to be.
Yeah, they're like a standardized shorthand. Absolutely essential. Standards cover this huge library of symbols for features, materials, manufacturing processes, components, welding symbols, surface finish symbols, electrical symbols. They all have very specific predefined meaning. It lets you pack complex instructions into a simple graphic, cuts down on text, reduces language barriers too.
Like icons on a car dashboard, yeah. Everyone knows what they mean instantly. Beyond the individual bits, is there a standard for the whole drawing sheet? The layout?
Yep, definitely. That comes under layout and presentation. Standards give guidelines for organizing the whole sheet. Where the title block goes, that's got the crucial info. Title, drawing number, who designed it, date, scale. How you track revisions so you always know you've got the latest version, that's critical. How drawing scales are shown, and just the overall arrangement to make it easy to read and find information.
And do the rules change depending on what kind of drawing it is? Say a simple part versus a, I don't know, complex machine assembly.
Precisely. The standards cover different drawing types. They have specs for things like individual part drawings, assembly drawings showing how all the parts fit together, schematic diagrams maybe for electrical or hydraulic systems, or architectural plans. Each type has slightly different needs to make sure it conveys the right information effectively.
Wow, it really is a complete language, isn't it? Are there any particular standards that stand out, like the main ones that hold it all together?
Yeah, the sources really highlight BS 8888. It's described as the sort of overarching standard for technical product documentation. It provides the framework for pretty much all aspects of technical drawings and the documents around them. And a really key takeaway is how closely it aligns with international ISO standards.
Ah, the ISO connection again. Okay, we definitely need to circle back to that. That sounds important.
Absolutely. And other key standards get mentioned too, the ones that dive deeper into specifics, like BSEN, ISO 128, that covers the general principles of presentation, those lines, views, sections we talked about earlier. And BSEN ISO 129 gives all the detailed rules specifically for dimensioning, tolerances, geometric tolerancing, all that. That EN ISO part. That tells you they're harmonized European and international standards. Often, the UK just adopts them directly as British standards.
Okay, so we've kind of mapped out what these British standards cover, this incredibly detailed rule book for basically every mark on the page. But let's zoom out a bit. Why? Why go through all this trouble? It feels like a lot of rules. What's the fundamental reason we use them?
That really is the crucial question, isn't it? And it's not about bureaucracy, not at all. It's about managing risk and, frankly, enabling complex stuff to actually get done properly.
So what's the single biggest benefit, the main payoff?
I'd say the most fundamental benefit, the one everything else builds on, is clarity and unambiguity. Standards just eliminate the chance of misinterpretation. Every line, every symbol, every dimension means one specific thing, defined by the standard. There's no room left for guesswork. Our sources hammer this home again and again. It's the primary defense against really costly mistakes in manufacturing or construction. If the drawing says, do this, everyone understands it means do precisely this.
Yeah.
No wiggle room in understanding.
Right. So it's basically about removing doubt.
Exactly. And that leads straight into the next big thing, consistency. When everyone's using the same standard language, a drawing made by one engineer in, say, London, can be easily read and understood by another engineer in Manchester, or a machinist on a factory floor somewhere else, or a builder on site. It just streamlines communication right across different teams, different companies.
And consistency, that usually means things get done faster, right? Efficiency.
Absolutely. Standards give a significant boost to efficiency and productivity. Designers, for example, spend less time worrying about how to draw something because the rules are set. They can focus on the actual design. And for the people reading the drawings, setting up machines, ordering materials, whatever, understanding is faster, more reliable. They're seeing a format they know.
Which must, in turn, just slash the number of mistakes and wasted effort.
Dramatically, yeah. Clear, consistent drawings directly lead to reduced errors and rework. If the instructions are perfectly clear, there's just far less chance of making parts wrong, assembling things incorrectly, or running into problems on a construction site. Minimizing rework saves unbelievable amounts of time, money, and materials. Think about the cost of scrapping a complex engine part or tearing down part of a building because someone read the drawing wrong.
Yeah, I can imagine. And I guess in some fields like aerospace or maybe medical devices, construction too, this isn't just a nice to have, it's probably legally required.
Often, yes. Legal and contractual compliance is a huge driver. In many industries, especially safety-critical or regulated ones, sticking to specific British standards or their international equivalents is mandatory. It's how you prove products or structures meet tough quality, safety, and performance criteria. It gets written right into laws and contracts.
You mentioned that ISO connection several times now. How does that global link actually work in practice? What does it mean day to day?
This is where the impact gets really big, actually. Because so many British standards are either identical to or very closely aligned with ISO standards. That's the International Organization for Standardization. It enables interoperability and global trade. It's massive. A drawing made to a BSEN ISO standard here in the UK can be sent to a manufacturer in, I don't know, Germany, Japan, China, and they can understand it and use it directly. No need for translation, no reinterpretation. The technical language is already universal. That enables seamless international projects, global supply chains. It's incredibly powerful in today's world.
Wow, so these standards literally act as bridges between countries.
They really do. And they also provide a vital base for training and education. Engineering schools, technical colleges, apprenticeships, they can all teach these standardized conventions. It means new engineers, new technicians entering the workforce are already fluent in creating and reading these crucial documents. You get a skilled workforce all speaking the same technical language from day one.
Okay, makes sense. And one last thing. How do you actually use the drawing to check if the final product, the thing you've built, is right?
Right. That's where they become the absolute benchmark for quality control and inspection. The drawing, with all its detailed standardized info, provides the precise criteria, what's acceptable, what's not. Inspectors can take the finished part, or measure the structure, and compare it directly against the drawing specifications. Verify dimensions, tolerances, features. It gives them completely objective standard to measure against. Pass or fail.
So when you boil it all down, what does this mean for you listening right now? It means that behind the scenes of pretty much every bit of engineered kit you use, every building you walk into, every manufactured product, there are technical drawings that follow these really strict, detailed standards. Every single line, every symbol, every dimension is telling a precise story, making sure things are built correctly, understood everywhere, and ultimately that they work safely and do what they're supposed to do.
Yeah, in essence, British standards and technical drawings, they're like this silent, indispensable language. It's what guarantees precision, what minimizes risk, boosts efficiency, and makes these complex global projects even possible.
They really are the kind of unseen architects ensuring precision and reliability in our technical world. So we've looked at what they standardize, everything from simple lines to the whole drawing layout, and we've explored the critical why driving that clarity, that consistency, and enabling global technical work.
And if you connect that to the bigger picture, it just really shows the incredible power of having a well-defined language that everyone agrees on and uses.
Which kind of leaves us with a final thought, something for you to maybe mull over. If a set of standards, seemingly just about lines and symbols on paper, can ensure something as complex as a jet engine part or a skyscraper is understood identically across the globe, what other areas of communication, maybe in your own life or in your work, could be radically improved if we just established a clearer, more shared understanding? A common language,